Welcome to Module 4, Lesson 15. Today where we will be solving area problems using scaled drawings. Okay, so an important note about area problems in terms of scale drawings. Okay, and again, this will come up later on, but I just wanted to put it out front here for you. So any area of A to the 1, okay, that just means the scaled drawing, the scaled A, okay, is k squared times the corresponding area, the original drawing. Okay, so what we've been used to finding is k. Okay, we've been finding k, which is the constant of proportionality. Okay, it's our scale factor. Okay, so when we're using any one-dimensional measurements, if we have a square, rectangle, for example, and let's say it's 3 units, this is 4 units. When we have calculated scale, of course we've got to compare one to the other, 1/3. Oh man, I don't know. Let's do this here, 6, make it easy. That doesn't make any sense, but let's do it. Oh boy, I said I wasn't going to waste any time this time. Let's see, 3, 4. Okay, I'm really making these up. You know that. Just trying to make a point here. But again, it is something we will see throughout this lesson. But anyway, so when we have a scale factor here, if we're going to actually scale down from here to here, of course, we can use our horizontal measurements. You know, that would be 4/8, and of course we've gone down by 1/2. That's our scale factor there. Okay, that is our k. Okay, that's our k. Is that in this case is that 1/2? All right, that's what we've done. We've scaled down from this larger rectangle to the smaller rectangle, and we've scaled down by 1/2. Scale factor of 1/2 or 50%, of course. Okay, but when we're talking about area, because we are talking about 2 dimensions, what all we need to do, and again, like I said, and continue to say, we will see this in exercises to come. All we need to do is actually take that k, that scale, that one-dimensional scale factor, and then go ahead and square it. Okay, so in this case, without doing any other calculations whatsoever, I would know that in terms of area, what I have done actually is I have scaled down to 1/4. Okay, therefore this new rectangle here has 1/4 the area of the original rectangle on which it was based. Okay, anyway, we're going to see this play out in a little while. Okay, and I think all right, so I forget what I do here beforehand. Okay. All right, here we go. So let's start. Okay, our opening exercise for each drawing, or for each diagram, drawing 2. Again, there will be a number of diagrams here. I think 1, 2, 3 different diagrams. Yep. Drawing 2 is a scale drawing of drawing 1. Okay. So you're going to go ahead and complete the accompanying charts below, side and area. Okay, so for each drawing, identify the side length, determine the area, and compute the scale factor. Okay, and you can see we're going to just fill in these 3 columns right here. Okay, and then we're going to convert each scale factor into fraction and percent. Percent, examine the results, and write a conclusion relating scale factors to area. Okay, I got in the way there. Couldn't see that there. Okay, so we're going to do all of these things. There's quite a bit to do. All right, and we're going to fill in this entire chart, and then we're going to also pay attention to filling in those 2 lines down there. Okay? Alright, so let's go ahead and begin. Alright, so if we're looking at the drawing 1, take our dimension measurements of drawing 1. We know that drawing 1, the side, okay, we can see it there, is 3 units. 3 units long. The area, therefore, okay, because it is a square, 3 by 3, okay, is of course, this is length times width, okay, looks like a 1, I'm trying to make that look like an L. Length times width, which is 3 times 3, which is 9 square units. Okay, again, just so you know where these are coming from, of course we had our 3 units here, which is the side, and then when I'm going to calculate area here, you know I do length. We do length times width, 3 times 3, which is 9 square units, which is this right here. Okay, so we have that done, and that's for side, for drawing 1. Okay. Now for drawing 2, you can see we have 9 units for our side measurements. Okay, and then we have an area of 81 square units, which is, of course, 9 times 9. And again, we need to know how to calculate area and know that very easily and very simply and very quickly for any of this to go smoothly. Okay. Now, the scale factor, we're going to come up with the scale factor here. We're going to calculate it as a fraction first, and then as a percent. Okay. And again, we're just going to plug in. You're going to see me write this 100 times or so in this lesson. But yeah, Q equals P times W. All right, to calculate our scale factor, or actually to solve for whatever we are missing. Okay, and but do that. Okay, and again, we are going from drawing 1 to drawing 2. Okay, very important, because that would make it, as you can see, an enlargement. Okay, which is going to be very, very different than a reduction. All right, so Q equals P times W. Therefore, 9, okay, which is the result of the scaling, okay, equals this percentage, whatever it is, times 3, which is the original side length, and then we just put 9 over 3 equals P, and so P equals 3 over 1, okay, so that as a fraction is our scale factor, and of course as a percent that would be 300%, okay, so this drawing 2 is a 300% scaled up drawing of drawing 1, okay. Alrighty, and then if we move on, we have Q equals P times W again. We're going to apply it to the area. Okay, so now we're having what's going to be called a quotient of areas. Okay, quotient of areas is the term they're using for this, and that's comparing the area of your original drawing to the area of your, the area of your scaled drawing to the area of your original drawing. Okay, so now we plugged in our new numbers, which is 81 equals P times 9. Okay, and then if we just follow that through, excuse me, 81 over 9 equals P, and that means P equals 9 over 1, which is our fractional value, or 900%. Okay, 900%, and yeah, you can see how that works out. And again, like I said, we will do this many times. But as was mentioned early in this lesson, if you to calculate this, what we're calling this quotient of areas, I'm not sure how often we call it that in this lesson, but quotient of areas, to actually calculate that, if you do remember, you took your one-dimensional scale factor, okay, and you squared it. Okay, so if I square 3 over 1, that equals 9 over 1, okay, which, of course, is right here. Okay, so that's how it works out. Again, you'll get more and more used to it as you see it and as you use it more, but just wanted to let you know how that will look. Okay, and again, our scale factor is 3, and our quotient of area is 9. Okay, and that could be expressed as either 9 over 1 or 900%. Scale factor the same, 3 over 1 or 300%. Okay, so here it is again. We have another diagram, and again we are moving from drawing 1 to drawing 2. And so what I'd like you to do, I'm going to pause here for a moment or a few minutes. No, I probably won't pause for more than a minute, but you do please pause and go ahead and do these calculations. Use what we've already worked with on the first problem and apply that here. Okay, it's the exact same idea. Okay, now we are looking in terms of the radius, as you can see right here. Okay, they're calling for radius and calling for area. Now, in terms of area, let me just go ahead and just clarify that when you are calculating area, just go ahead and do it in terms of radius, radius squared times pi. Okay, just keep pi by itself. So just have your answers here in the area part in terms of pi. You don't need to. Do not use 3.14 and do any calculations. Okay, in that sense. Okay, we don't need to do that. All right, go ahead and give it a try, and then come on back. Okay, well, let's see how it went. All right, so again, we're looking at drawing 1. We're going from drawing 1 to drawing 2. Our radius for drawing 1 is 4 units. Again, I just counted those units. Now I'm going to drawing 2, 8 units. So you can see I'm taking this a little bit differently. I'm working across, working horizontally here. Going ahead and create my scale factor now, going from drawing 1 to drawing 2. Again, as you can see, this becomes probably very, very natural for many of you. Q equals P times W. Therefore, 8 equals P times 4. And of course, 8 over 4 equals 2 over 1, which equals 200%. Okay, and so that is my scale factor as both a fraction and a percent going from drawing 1 to drawing 2. Okay. Area, going to be a little bit different. Now, area of a circle equals pi, like I said, pi times r squared. Okay, but we're going to just keep this in terms of pi. All right, so pi times r squared, and so in this case we have r squared, which is 16, okay, because radius is 4. All right, and so then we're just going to put 16 pi square units. Okay, we're just going to express it that way. Hopefully that's how you did it. We don't need to do our 3.14. It's just going to take us into, again, we will do this eventually, but for now it's just going to take us somewhere where we don't quite need to be yet. Okay. All right, in terms of drawing 2, same idea. Pi times r squared, and then so that's pi times 64, because 8 squared is 64, and then we're just going to put that as 64 pi square units. Okay, so what that means, of course, is 64 times pi would give us our number of square units, but for now we're going to leave it just as written in these terms. Okay. And it makes it seem, it's a little bit more clear now to the point we're trying to prove, as you can see, when we go ahead and create our scale factor, or our quotient of areas. You can see that this 16 is going to compare well with this 64, whereas otherwise it wouldn't have been as clean. Okay, so we go ahead and do that, and we have 64 pi squared equals P times 16 pi squared, and 64 over 16 equals 4 over 1, or 400%. Okay, and so 400% is the scale factor going from the area of drawing 1 to the area of drawing 2. Okay, all right, so we're down here. We have our scale factor is 2, and our quotient of area is 4. And hopefully, might become obvious here now to you. You start seeing some pattern. If you noticed here, we went. This is the first one. I just switched back, hard to tell, but this scale factor here was 3, and it went up to 9, Okay, what is that? That's 3 squared equals 9. Over here, if you look at here, we're from 2 to 4, and this, of course, was 2 squared. Again, that relationship is, we're building this relationship between one-dimensional scale factor and a two-dimensional scale factor. Okay, here we go. We have our third diagram, and just to let you know, up top here it says we have the length of each side, and drawing 1 is 12 units, and drawing 2 is 6 units. Okay, so just going to give you that, and again, you're still going from 1 to 2. Okay, and as you can see now, it is a reduction. Okay, the 2 prior examples were both enlargements. So I'm going to pause right now, have you work through this by yourselves, and come on back and check in. Okay, so let's check in and see how you did. Again, we're going from drawing 1 to drawing 2, a reduction. All right, and just filling in, we have 12 units for my sides of drawing 1 and drawing 2, 6 unit sides. All right, so I'm working across here now. I'm going to figure out calculate a scale factor for my side measurements, which happen to be one-dimensional measurements. Q equals P times W. 6 equals P times 12, which is 6 over 12 equals 1/2, which equals 50%. Okay. All right. So now, and it's pretty obvious, and it makes sense. It's reasonable. It's a reduction, and happens to be a 50% reduction. Okay. And of course, 12 and 6 compare. 6 is half of 12. Okay. It makes sense, and hopefully, you can. I want you to use this formula as often as possible, but you are starting to see, hopefully, beyond that formula, and just being able to look at these numbers and say, hey, this just makes very good sense, doesn't it? Okay. Let's look at area. Okay. So in terms of area, we are now going to calculate our area of our first square, which is 144 square units. Okay, drawing 2 is going to have 36 square units. Okay, and now we're going to compare those using our Q equals P times W. 36 equals 144P, and then 36 over 144 is the same as 1/4, which is the same as 25%. Okay, 25%. And we are going to have a scale factor of the one-dimensional aspect of these two drawings is 1/2 or 50%, whereas the quotient of the areas is 1/2 squared, or 1/4 scale factor, or 25%. Okay, and again, here is the key right here. Is this idea is that we've just taken our scale factor, one-dimensional scale factor, and squared it to get our two-dimensional scale factor. And that pretty much is the conclusion part that they were asking about. Okay, it's the same. Oops, sorry. Yeah. So, yeah, and there it is. The conclusion is, and again, I told you already, I told you at the beginning of the lesson about this idea of your two-dimensional scale factor being the one-dimensional scale factor squared. Okay, but that's kind of where we were getting to. Wanted you to see that as we went through all of these problems that that was the case. Alrighty, so here we go. We have example 1. Now, example 1 asks us this question: what percent of the area of the large square is the area of the small square? Okay, so you have all that you need right there to figure this out. Use what you've learned, and come on back when you feel you have the answer to this one. Okay, I'm going to pause. Okay, well, let's see how you did here. All right, so again, we are looking at area. Okay, so easy enough to get fooled and thinking in terms of one dimension. Okay, but we're looking at area. All right, and here are the measurements we'll need. Our larger square is a 5-unit square. Okay, 5-unit sides, and the smaller square has 1-unit sides. Okay, so therefore we can just go ahead and okay, and again we're just saying now this is what percent of the area of the large square is the area of the small square. Okay, so we are looking at a reduction. Of course, we're going from the large square to the smaller square. Q equals P times W. Okay, so 1 equals 5. Now you see what I'm just remembering now what I did. So what I've actually done here is I have not actually gotten the area first. What I've done is I've actually taken the side. Okay, this is one method of doing this. You may have done it differently, and that's fine. But what I've done is I've taken the side measurement and found the scale ratio of the scale factor, excuse me, of the sides, the one-dimensional measurement. And now what you'll see, there we go, that is the one-dimensional scale factor, is that 20%. Okay, now all I need to do is go ahead and square that that one-dimensional scale factor, and always working with the fractional portion of it. It's much easier. Okay, and then what I get is yeah, there we go. So we have our one-dimensional scale factor is 20%, and two-dimensional scale factor here is going to be 4%. Okay, and you can see how that works right here. Okay, because when I square this, I get this, which is equivalent to that. Okay, you could have done it differently. Maybe you went ahead and found the areas first. You could have found the area of the large rectangle or large square was 25 square units versus 1 square unit. And as you can imagine, it's pretty easy to see that, or to imagine that. See here we have one unit squared, and we'd have 25 units squared. Pretty easy to see that this smaller square is 1/25 of this larger square. Okay? Alright, yeah, a couple ways to do it. I like doing it the one-dimensional way. It's pretty quick, and all I need to do is just square my answer. Yeah, so one-dimensional versus 2D. Okay, that's the way I approached it. Alright, example 2 here. What percent of the area of the large disk lies outside the smaller disk? Okay, and you can go ahead and let's just use, I would just let you know, let's go ahead and use a radius. Okay, use your radius to find out the measurement to use would be your radius. Okay, so go ahead and work with that first. I'm going to tell you. So try to do this one, example 2, as I did example 1, working with that one dimension, and then extrapolating to the 2 dimension using the squaring process. Okay, so go ahead and give that a whirl, and come on back. Okay, let's see how you guys did. Alright, again, we're talking about area. Alright, but don't actually need to calculate area. Okay, this is what I was asking you to keep in mind and to use, because I want you to try to use this strategy. Again, it kind of brings to the forefront the whole relationship between scale factor, one-dimensionally and two-dimensionally, and it's also easier, especially when you're dealing with having to deal with pi. Okay, so here we go. So all we need to do, therefore, is to go ahead and calculate our well, we can use, actually, I said to use to radius, but truth is, all we really need, we could also use diameter. It's be a very similar measurement, okay? So I'm using diameter, all right? 8 to 4, okay? And we are trying to find out what percentage of the area of the large disk lies outside the smaller disk, okay? So we have 4 over 8, okay? So 4 over 8 is 1 over 2, okay? Because we're actually trying to find out how that small disk is related to that large disk, and that's 1 over 2. And then if we go ahead and just go ahead and square it, okay, square that factor, because this is the scale factor as it stands as a scale factor of the one dimension of that one diameter dimension, okay. So then we're going to go ahead and square that, because that's how we get the scale factor of the area. And we get 1/4. 1 over 4 is our scale factor of the area, and that is 25%. So in terms of area, this small circle is 25% of that larger circle. Okay, let's see what's going on next here. All right. So example 3. If the area of the shaded region in the larger figure is approximately 21.5 square inches, write an equation that relates the areas using scale factor and explain what each quantity represents. Okay? So we can start with scale factor, okay, of the corresponding sides, all right? And then what you're going to eventually do here is we are going to, well, firstly we're going to write an equation that relates the areas using scale factor and explain what each quantity represents. Then we're going to determine the area of the shaded region in the smaller scale drawing, okay, in that smaller scale drawing. All right, so let's go ahead and have you work on that. And again, persevering, looking at a problem that may not seem also very clear at the beginning, but persevering and figuring it out. Okay, all right. So go ahead and give it a whirl. I know I've taken you back to the prior problem here, because I realized that we never did actually finish this or answer this question, because the final question here was what percent. I'm going to take this over. I think I put so much highlighting on these things sometimes that I forget what I'm actually trying to answer here. But yeah, this is a good example of answering the question that's asked, actually. So what percent of the area of the larger disk lies outside the smaller disk? Okay, so we've actually figured that this was 25%. The small disk was actually 25% of that larger disk. Okay, therefore we have one more step to take. Okay, and that would just make sense that, therefore, if this here, this represents 25% of that larger disk, therefore 75%, this would be our final answer, 75% of the larger disk lies outside the smaller disk. Okay, so I've brought you back here to the prior problem, okay, this example 2, because what I did not do, actually, is actually answer this question, okay? And the question was, what percent of the area of the large disk lies outside the smaller disk, okay? What we did answer, okay, was that this here, this smaller disk, represents 25%, okay? 25% of the larger disk. Okay, therefore, if that represents 25% of the larger disk, then the answer to the question is the larger disk that lies outside. So it's all of this is what we're actually asked to answer, and that is actually, of course, 75%. All right, so 75% of that larger disk lies outside the smaller disk. Okay, and that is actually the answer. Sorry if that caused any confusion. What happens sometimes when I cut and paste these pages on the slide, you can see I actually missed some things, and there was that last little question that was about area outside shaded disk, which is just a bad excuse, I guess, because the question was pretty clear. So answer the question, all right? Okay, there we go. And yeah, let's move on. And here we are back here again. And let's go ahead and work this one out. Okay, so again we are writing an equation that relates the areas using scale factor. Okay, we're going to explain what each quantity represents, and then we're going to determine the area of the shaded region in the smaller scale drawing. Okay, so let's go ahead and start with that. Now we know that this area is 21.5 square inches. Okay, and again it's the area of the shaded region. Okay, the shaded region, because we can tell, okay, we know that the area of this entire square, including the circle that's been lopped out of it, would be, of course, 10 times 10, okay, because it is a square here, okay. Well, I guess they don't tell you it's a square, but anyway, let's take that off. But you can see that it would have been a lot more. If that was a 10 by 10 square, it would be 100 square inches, would be the actual area of area of all of this, okay, would be somewhere near 100 square inches. Therefore, we can just understand that this 21.5 inches refers only to the shaded part. This part's in blue. Okay, but really real interesting though is that we really don't need to mess with all the rest of it, because our scale factor is going to help us tremendously. Okay, this is this figure here, the smaller figure, is a scale drawing of the larger figure. Therefore, all of its ratios, okay, that means the ratios of everything, okay, so the ratios in terms of the shaded area, the ratios in terms of the circle inside, okay, are all going to remain consistent, okay, in a one-dimensional point of view. So let's go ahead and just figure out our scale factor, okay. So the scale factor of the corresponding sides is 3/5, okay, 3/5, which is the scale factor as a fraction, okay, and again, that is just using our 6 inches here and putting it over the 10 inches. That's where I get my 6/10 from, and I get 3/5, which is a scale factor. Okay, so the area scale factor, therefore, is going to be that. And again, I didn't need to do this as a percentage, but if I did do this as a percentage, of course, this is going to be 60%. Okay, which makes sense because it is a reduction. But now, if I'm going to figure out my area scale factor, okay, you can remember that I just take that scale factor right here, 3/5, and I square it. Okay, which I'm doing right here. And this is the relationship we found out, okay, and that's really important that we have that down. I don't want to have you questioning constantly, why it is, but just know that it is, okay, because when we go from one dimension to 2 dimensions, you are now having to square the one-dimensional scale factor, because when you are finding area, you are squaring the one-dimensional one-dimensional lengths. That's exactly what you're doing. Okay? So yeah, we'll go ahead and do that, and then we get 3 over 5 times 3 over 5, because that's 3 over 5 squared. That equals 9/25. Now that 9/25, okay, this here is our area scale factor. Okay, so that means this small figure here is 9/25 of the larger figure here. Okay, larger drawing. All right. So the question is, the final question here is determine the area of the shaded region in the smaller scale drawing. Now we could not have used this scale factor here to determine the area of the shaded region in the smaller scale drawing, simply because this was a one-dimensional scale factor. Okay, we needed to go and find this first, and now we can apply our 9/25 area scale factor and come up with the area of the shaded portion of the smaller figure. And if we do that, all we need to do is multiply, and that's that 21.5 over 1, which we get from here. Okay, that's the area of the larger, and apply or multiply it by our scale factor, okay, our percentage, which is 9 over 25, and we get an answer of 7.74 square inches. Okay, and again, that is the area of just this shaded region. Okay, and which is nice. And if you notice, we did not have to do at all in this. We did not have to figure out the area of this the circle. Okay, we could have. We could have figured that out and subtracted it away from the larger. But no, it's just to show you another way that we can apply scale factor, in this term's area scale factor, to make our lives a lot easier. And that's pretty much what we try to attempt in math is, if I could emphasize that, is to just make your life easier. Okay? All right, so let's move on to the next. Okay, so here we are at example 4. Okay, so we are going to use figure 1 below and the enlarged scale drawing, okay, to justify why the area of the scale drawing is k squared times the area of the original figure. Okay, and we're just going to go ahead and do this together. Again, excuse me. What they're trying to emphasize here is getting you to justify this. So it's powerful to be able to justify a rule, okay? Because our rule here is, you know, if we're going to use scale on a one-dimensional basis, we just square that scale actually to get in terms of 2 dimensions. All right. So that's what you can see, because you can see right here, and again I'll go through it all, but the point here is that you have figure 1, and you have W and you have L, which are length and width. Okay. Now what you're applying to each of those length, to that length and to that width, is this factor K. Okay, that's scale factor K. Okay. So to get area, of course, you're going to multiply. So you're going to multiply in figure 1. You're going to multiply L times W. Okay. I just hate the way that looks. I'm going to make it look more like an L. L times W there. But now, with the next figure, you're going to be multiplying KW by KL. Okay. And you can see what's going to happen here. All right. So what they're trying to do is they're trying to get you to look at this a number of different ways, just so it can you know, further cement in your understanding this idea of how we use a squaring factor when we're talking in terms of area. So I'm just going to erase all these strokes and then just start over again, because I did make some strokes before today. So let's go ahead and work through those. All right. And again, we're trying to justify why the area of the scale drawing is k squared times the area of the original drawing. All right. So we have the area of figure 1 equals L times W, and again I'm pretty much rehashing what I just said, but I want to say it enough times and in enough different ways, that it'll be easier to understand. Okay, and again the area of figure 2 is KL times KW. Okay, and again that K, of course, stands for the scale factor. Okay, that scale factor, whatever it may be. Again, we don't have any lengths or any widths, so we have no measurements here, okay, whatsoever. So we're not going to calculate any kind of scale factor here. But if we did, that's what that K would be standing for. So same as K squared times LW. So the way this is written here, KL times KW, which of course is just simply this times this, which makes sense, length times width, all right, is the same as this here, okay? Is the same as just taking this length and this width, okay, which is the area of figure 1, and multiplying it by the scale factor squared, which is exactly what we've been doing, okay, over and over and over again, all right? And you can see it just play out here. It's kind of a nice way to look at it, to see it, maybe to justify it in your own mind, and to help you make some more sense of it, because that's exactly what we're doing. Okay, we're just applying this scale factor, which is K, and then when we multiply a length times a width, we would actually be squaring that K, because that K would be multiplied by itself. All right. So again, let me just see what different strokes I have, because I know I'm making a big mess. Okay, so explain why the expressions K times L times K times W and K squared LW are equivalent. Okay, and so how do these expressions reveal different information about the situation? So let's go ahead and justify this. So K shows that both the length and the width of the scale drawing, number 2, are multiplied by the scale factor. Okay, that's what they show. And again, I think I just said this, but like I said, I did these strokes last night, and now I'm doing my voiceover today, so I'm going to repeat myself over and over again. Anyway, yeah, so that's what that shows. Okay, that it's showing that both the length and the width of the scale drawing are multiplied by the scale factor. Okay, and actually that's not true. It's actually the both the length and the width of the original drawing. Okay, this is the original drawing. See, it's always nice to do things over. Yeah, because we're taking actually this L and this W over here, and we are applying the scale factor to them. Okay? All right. And K squared shows how we need to attend to the 2 dimensions of area. Okay? K squared. Excuse me. If we are multiplying L times W to get area, we are going to multiply that scale factor by itself, because it applies to both the length and the width. Okay? All right, so I'm going to erase all this, and I want to just show you how this plays out and how this looks in an actual example. Okay, and that'll make it even more clear. If it's not clear already, I really do hope it's not clear as mud, as they say. The more clear as a clear mountain stream. Anyway, here we go. So let's plug in some numbers for our variables and check. Okay, let's go ahead and say that our K, or our scale factor, is 4. Okay, which means that it's 400% enlargement. Okay, I'm just making this up. This is just hypothetical. And let's say we have a length of 10 and a width of 6 in our original figure. Okay, so let's plug this in. All right. So if we do plug it in, we have, and we're going to do it this way, K times L times K times W. Okay, and that would be 4 times 10. Okay, because the, well, let me go ahead and explain that. So here's the 4 is, of course, the K is the scale factor, and then the 10, in this case, is the length. Okay, we're talking about the original. And then we have the 4, again, the scale factor, times the width. Okay, so these apply, these work right here. These are just those there, just played out with an actual example. Okay, so let's go ahead and figure that out. That would be 40 times 24, which is 960. Okay, so that's what the value is of KL times KW when we plug in these values. Okay, now let's go ahead and do the same for K squared times LW. Okay, now we have K squared, which is going to be 4 squared, because you can see our K here, our scale factor is 4. Okay, and then L times W is 10 times 6. All right, and if we go ahead and play that out, that would be 16 times 60, which is also 960. And I wanted to go ahead and show you that these are the same, 960 and 960. So whichever way I look at it, if I look at it as KL times KW, okay, right there, KL times KW, all right, I get 960. If I look at it as K squared times LW, I get the same 960. Okay, so we have actually justified it, hopefully. I know may not be as clear as I want it to be quite yet, but we have justified why we do indeed square our original scale factor to apply to area. Okay? Well, let's move on to the next. Here we go. Exercise 1 here, we have the Lake Smith basketball team had a team picture taken of the players, the coaches, and the trophies from the season. Now the picture was 4 inches by 6 inches. Okay, and this is a lot of fun. This is actually there's several questions that actually up to G, A through G here, and then we close. So this Lake Smith basketball team problem is going to take us right to the end. So what I want you to do, and again I'll just continue reading it, but what I would like you to do is just to go ahead and muddle through A through G. Do the best you can. Pause after when I tell you to pause. Do the best you can, and then come on back and do the best you can to persevere. Come on back, and we will go through it all. But anyway, let's go ahead and get you started here. So the picture, this original picture, was 4 by 6, 4 inches by 6 inches. All right. Now the team decided to have the picture enlarged to a poster, and then enlarged again to a banner measuring 48 by 72 inches. Okay. Now the first thing they want you to do, and we can do this together, is, and I'll start you here, sketch drawings to illustrate the original picture and enlargements. Okay, so the only, the original picture we're going to have, we have some dimensions, okay, and we have dimensions of the end. What we don't have dimensions of are that poster in between. But let's go ahead and just draw this picture. Okay, so again, using what we know, here's our picture, and it's a 4 by 6. And that leads to, or it's enlarged to a poster, which we don't know, whose dimensions we don't presently know, which is then enlarged again to a banner, whose dimensions are 48 by 72. So I'm going to get you there. What I want you to do is go ahead and do the best you can, persevering through A through G, and then come on back after you're all done, and we'll go through each of those one at a time. Okay, let's take a look. Hopefully you did well and you're persevering. All right, so B asks us if the scale factor from the picture to poster is 500%, determine the dimensions of the poster, okay, of the poster. So not area yet. So we're not looking at area yet, just to make sure that we understand that. Again, you look at a picture, you look at a poster, you look at a banner, and for me, I just see area, But what we want to do is we want to figure out a scale factor, a one-dimensional scale factor. okay? And to do that, we have our picture and our poster. I'm making a little chart here just because I want to remember, because my picture is on the page before this, all right? So we have a picture of 6 inches in length, okay, 6 inches in length. We have the poster, which is 500% enlarged, okay, and that's where these numbers come from. We have, again, our picture is in inches, 6 inches here. Our scale factor to the poster is 5, okay, which is same as 500%. Therefore, I can go ahead and figure out my poster length, okay, is 30. So I'm able to apply my scale factor to start figuring out, putting some of these puzzle pieces together from the picture to the poster, okay? Next, let's work on the width. Again, the same idea is we are going to apply our scale factor of 5, okay, to the 4-inch width, and that would leave us with a 20-inch width for our poster. Okay, so we know our poster now is 30 by 20. Okay, so now C asks you what scale factor is used to create the banner from the picture, okay, which is a lot of fun because we have all of those dimensions, all right, and all we need to do is work back to the scale factor. And again, what these problems do over and over again is they present you with different pieces of information. Okay, so you might have a scale factor that you know, like we knew in B. We knew the scale factor, we're able to apply it. But in this case, we know all of the dimensions, but now we need to work towards that scale factor. Okay, all right. So again, to the banner from the picture being our original. Okay, let's go ahead and just plug the banner in there. All right, and just put those that we know. We knew we had 72 by 48. And if we create our Q equals P times W formula again, we have 72, which is the banner length, is some percentage of the picture, which is 6. And if we go ahead and do our math there, we get 12. Okay, so we have a scale factor of 12, which is 1,200% or 1,200%. Okay, please don't think it's 12%. All right, it's that's easy to fall into. Excuse me, because this first number we get here, whenever it is a whole number, okay, it is on the left side of that decimal point. So we are looking at more than 100%, or in this case, over 1,000%. Okay, so that banner was a 1,200% scale factor to get to from the picture to the banner. As you can imagine, that's quite a difference. Okay, so D asks us, just moving along here, D asks us what percent of the area of the picture is the area of the poster. So now we are into to the realm of area. Okay, and justify your answer using scale factor and finding the actual area. Okay, so now we have scale factor, all right, which is 500%, which is a scale factor of 5. Okay, so from the picture, what percent of the area of the picture is a poster? We have that scale factor, which was up there in B. Okay, so we need to apply that. We're going to apply that scale factor of 5, and therefore you're probably thinking about it already. And scale factor applied to area is 5 squared, okay, or 25, or 2,500%, okay. So that area of the poster, the area, is a scale factor of 25, or actually 2,500%, the area of the picture. Okay, again, all we've done is taken our scale factor, our one-dimensional scale factor, and we have squared it to get our two-dimensional or area scale factor. Okay, E. Write an equation, okay, involving the scale factor that relates the area of the poster to the area of the picture. Okay, all we want now here is we want an equation, okay, just going to relate the area of the poster to the area of the picture, okay. Q equals P times W is our chosen formula, and in terms of relating what those Q's and P's and W's actually stand for here, the area of the poster is going to stand as our Q because it is what is the result of the application of a scale factor. Okay, and of course we have our percentage, and then of course our area of the picture is stands for our W, which is also stands for our original measurement. Okay, and that is our, and here is that. So A equals 25P. Okay, so that equation right there is A, the area of the poster, which A stands for, equals 25P. So whatever that poster size, if we wanted to use that same scale factor, all we would have to do is, let's say we wanted to do a 8 by 12 picture. We could just apply that 8 by 12 picture and just apply the scale factor. Okay, the scale factor, and we would know how large we would need how large our poster would be scaled up. Okay. All right. F. Assume you started with the banner and wanted to reduce it to the size of the poster. What would the scale factor as a percent be? We have all the information we need. All we need to do, again, which turns out to be one of the most important things, is to plug these numbers into the right place. Okay. Again, as I promised before, you've seen this Q equals P times W several times now. One more time. Here we go. And we have our poster dimension equals P times a banner dimension. Now we can choose either one we want. Again, we're looking for a scale factor. Okay, looking for a scale factor. So we could just take a horizontal or a vertical dimension, whichever one we wanted to do. And let's go ahead and take, I think this is the length, right? So we have a poster dimension, so 30 inches equals or is the same as some percentage times 72, which is the banner length. All right, and again I just put 30 over 72, which gives us 0.416666, repeating, all right, which we would express in the end percentage-wise as 41 2/3%. Again, using that, opting to use a fractional representation here when you have this repeating decimal here. Okay, that's why we opt to do that. Makes it a little bit more, or somewhat more accurate. Okay, if we were going to do any kind of calculating, we'd probably want to use this fraction or a reduced fraction. Okay, but anyway, yeah. So now we find out what the scale factor would be if we went from the banner to the poster. We would be reducing it, and it would be 41 2/3% of the size of the banner, this poster. Okay. All right, what scale factor then would be used to reduce the poster to the size of the picture? Okay, now we're trying to find out what scale factor going from poster to picture. Okay, and again, one more time, Q equals P times W. The picture width, let's go ahead and compare that to the poster width and apply a percentage, and that percentage is going to be the one we're solving for. 6 equals P times 30, which goes to 6 over 30, which equals, this is the same as 1 over 5, which is 20%. Okay, so going from the reducing the poster to the size of the picture, so working backwards from the way we had worked originally, that would represent a 20% reduction. Okay, and again, very, very important, and hopefully you're catching on. Very different to go from that smaller picture up to the poster. That percentage is going to be very different than going from the size of the poster back to the picture and that reduction. Okay, you can see those differences hopefully. Okay, lesson summary here. If the scale factor is represented by k, then the area of the scale drawing is k squared times the corresponding area of the original drawing. Very simple lesson summary, but something that has come up again and again and again. Again, if we had a one-dimensional scale factor of 1/2, okay, or 50%. Okay, if we had a scale factor, so that means that was a reduction. We went from something that was larger to something that was, excuse me, smaller. If we had that one-dimensional scale factor of 1/2, very simply, if we're going to talk in terms of 2 dimensions, or area, okay, we would just take that 1/2, that a scale factor, the original one-dimensional scale factor, and we would just square it, okay, and that's going to equal 1/4, or 25%, okay. So, to look at this a little bit more closely, what this is saying is that well, actually, let's start from here. So this dimension, or this length there, is 50% of this length, okay? But, and this area is 25% of this area, okay? So it doesn't work the same. It's not, if you're taking a one-dimensional measurement, okay, such as the length here, okay, that's going to have a different scale factor than comparing the areas of these same 2 pictures, okay. Very, very important. Might not be absolutely obvious to you yet, but I trust that you are all going to get there. Okay, well, thanks for bearing with me. We are over an hour. So sorry. Hopefully you can not have to spend too much more time on this. All right. Okay, we'll see you in lesson 16.